In NEC Chapter 9, Table 9, each wire size has two lines because they represent different conductor materials, specifically copper and aluminum. The National Electrical Code provides this distinction to account for the varying electrical and physical properties of these two materials. The first line corresponds to copper conductors, while the second line corresponds to aluminum conductors. Copper is a better conductor of electricity than aluminum, meaning it offers less resistance to the flow of electrical current. This characteristic results in a higher ampacity rating for copper conductors of the same size compared to aluminum conductors. Ampacity refers to the current carrying capacity of a conductor, or the maximum amount of electrical current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. Aluminum, on the other hand, is lighter and generally less expensive than copper, making it a suitable alternative in certain applications where weight or cost is a significant factor. However, due to its lower conductivity, aluminum conductors require a larger cross-sectional area to carry the same amount of current as copper conductors. Table 9 provides essential information for selecting the appropriate conductor size based on the material and the anticipated current load. It's crucial to consult this table to ensure compliance with the NEC and to maintain a safe and reliable electrical system. The table also considers different types of insulation used on the conductors. Insulation materials have varying temperature ratings, which affect the ampacity of the conductor. Higher temperature rated insulation allows conductors to operate at higher temperatures, thereby increasing their ampacity. NEC Table 310.13 and its associated tables, such as 310.16, 310.17, and 310.18, provide detailed ampacity ratings for conductors based on insulation type, ambient temperature, and the number of conductors bundled together. It's essential to consider these factors when selecting conductors to ensure they can safely carry the intended current without overheating. When using Table 9, always refer to the specific application and the relevant sections of the NEC to ensure proper conductor selection and installation. Incorrectly sized conductors can lead to overheating, insulation damage, and potentially hazardous situations, such as electrical fires. In addition to ampacity, Table 9 also provides information on other conductor properties, such as resistance and reactance. These properties are important for calculating voltage drop and ensuring efficient power delivery. Voltage drop refers to the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, it's important to select conductors with a sufficient cross-sectional area. The NEC provides guidelines for acceptable voltage drop limits in various types of circuits. For example, the NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. By considering conductor properties and ampacity ratings from Table 9, engineers and electricians can design and install electrical systems that meet the requirements of the NEC and provide safe and reliable power distribution. Remember that the NEC is a comprehensive set of standards that is updated regularly to reflect advancements in technology and best practices in electrical safety. Therefore, it's essential to stay up to date with the latest edition of the NEC and to consult with qualified professionals when designing or installing electrical systems. Copper conductors are generally preferred for their superior conductivity, which allows them to carry more current for a given size, reducing voltage drop and improving energy efficiency. They also offer better corrosion resistance and are easier to work with due to their flexibility and ductility. However, copper is more expensive than aluminum, which can be a significant factor in large-scale installations. Aluminum conductors, while having lower conductivity, are lighter and more cost-effective. They are often used in overhead power transmission lines and large feeder circuits where weight and cost are major considerations. However, aluminum conductors require special connectors and installation techniques to prevent corrosion and ensure reliable connections. Aluminum oxide, which forms on the surface of aluminum when exposed to air, is an insulator and can impede electrical conductivity. Therefore, it's crucial to use oxide-inhibiting compounds and proper termination methods when working with aluminum conductors. The NEC provides specific requirements for the installation of aluminum conductors to address these concerns. For example, NEC Section 110.14 covers the requirements for making electrical connections, including the use of listed and labeled connectors suitable for the specific conductor material and application. In addition to Table 9, other tables and sections of the NEC provide valuable information for conductor selection and installation. For example, NEC Table 310.16 provides the allowable ampacities of insulated conductors rated up to 600 volts based on their insulation type and ambient temperature. NEC Section 310.15 outlines the requirements for conductor ampacity adjustment and correction factors, which are used to account for factors such as ambient temperature, the number of conductors in a raceway or cable, and the presence of harmonics. When selecting conductors, it's important to consider the entire electrical system and the specific requirements of the application. Factors such as the load characteristics, the length of the circuit, the ambient temperature, and the presence of corrosive environments can all affect conductor selection. Consulting with a qualified electrical engineer or electrician is recommended to ensure that the selected conductors meet the requirements of the NEC and provide safe and reliable performance. Remember that the NEC is a minimum standard, and it may be necessary to exceed the requirements of the NEC in certain situations to ensure optimal performance and reliability. For example, using larger conductors than required by the NEC can reduce voltage drop and improve energy efficiency. In summary, the two lines in NEC Chapter 9, Table 9, distinguish between copper and aluminum conductors, providing essential information for selecting the appropriate conductor size based on the material and the anticipated current load. Understanding the differences between these materials and following the requirements of the NEC are crucial for ensuring the safety and reliability of electrical systems. Always consult the latest edition of the NEC and seek guidance from qualified professionals when designing or installing electrical systems. The selection of copper versus aluminum conductors depends on a variety of factors including cost, weight, conductivity requirements, and environmental conditions. Both materials have their own advantages and disadvantages, and the optimal choice depends on the specific application. Consider a scenario where you are wiring a residential building. For branch circuits feeding lighting and receptacles, copper conductors are generally preferred due to their superior conductivity and ease of installation. However, for the main service entrance conductors, aluminum conductors may be considered to reduce costs, especially for larger conductor sizes. In industrial applications where large amounts of power are distributed over long distances, aluminum conductors are often used for feeders and service entrance conductors due to their lower weight and cost. However, copper conductors may be used for critical circuits where reliability and performance are paramount. In corrosive environments, such as chemical plants or marine facilities, special considerations must be taken to protect conductors from corrosion. Copper conductors generally offer better corrosion resistance than aluminum conductors, but both materials may require additional protection, such as corrosion-resistant coatings or enclosures. The NEC provides specific requirements for the installation of conductors in corrosive environments. For example, NEC Section 300.6 requires that raceways, cables, and enclosures installed in damp or wet locations be made of corrosion-resistant materials. When working with aluminum conductors, it is essential to use proper termination methods to prevent corrosion and ensure reliable connections. Aluminum oxide, which forms on the surface of aluminum when exposed to air, is an insulator and can impede electrical conductivity. Therefore, it is crucial to use oxide-inhibiting compounds and listed and labeled connectors suitable for aluminum conductors. The NEC provides specific requirements for making electrical connections, including the use of connectors listed for the specific conductor material and application. In addition to conductor material, the insulation type also plays a significant role in determining the ampacity of a conductor. Insulation materials have varying temperature ratings, which affect the maximum temperature that the conductor can withstand without degrading the insulation. Higher temperature rated insulation allows conductors to operate at higher temperatures, thereby increasing their ampacity. The NEC provides ampacity tables for conductors with different insulation types, such as THHN, THWN, and XHHW. These tables are based on the assumption that the conductors are installed in a specific manner, such as in free air or in a raceway. When conductors are installed in a manner that restricts their ability to dissipate heat, such as when they are bundled together in a raceway, their ampacity must be derated to account for the increased temperature. The NEC provides ampacity adjustment and correction factors for various installation conditions. It is important to apply these factors correctly to ensure that the conductors are not overloaded and that the insulation is not damaged. In addition to ampacity, other conductor properties such as resistance and reactance are also important considerations in electrical system design. Resistance is the opposition to the flow of electrical current, and reactance is the opposition to the flow of alternating current due to inductance and capacitance. These properties affect the voltage drop in a circuit, which is the reduction in voltage along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for acceptable voltage drop limits in various types of circuits. For example, the NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to select conductors with a sufficient cross-sectional area and to keep circuit lengths as short as possible. In summary, the two lines in NEC Chapter 9, Table 9 provide essential information for selecting the appropriate conductor size based on the material and the anticipated current load. Understanding the differences between copper and aluminum conductors, as well as the factors that affect conductor ampacity and voltage drop, are crucial for ensuring the safety and reliability of electrical systems. Always consult the latest edition of the NEC and seek guidance from qualified professionals when designing or installing electrical systems. Firstly, copper offers superior conductivity compared to aluminum, allowing it to carry more current for a given size. Secondly, copper exhibits better corrosion resistance, making it suitable for a wider range of environments. Thirdly, copper is generally easier to work with due to its flexibility and ductility. However, one should be aware that copper is more expensive than aluminum, which can be a significant factor in large-scale installations. Aluminum, on the other hand, is lighter than copper, making it advantageous in applications where weight is a concern. Aluminum is also more cost-effective, making it an attractive option for large-scale projects. One must know that aluminum requires special connectors and installation techniques to prevent corrosion and ensure reliable connections.